Hi everyone, this is Cheska Loretizo from BS Electronics Engineering 3A, and now I'm going to report about NBDD waveform diagram. So first, this is the diagram, and it shows that in letter A diagram, the topology of the output stage. Letter B, the time domain waveforms of the output of the modulator and amplifier. C. Block diagram of the extended NBDD PWM modulator. D. Floating gate driver with galvanic isolation of the control signal. So next, the control signals contain dead time between the switch states where all switches are off to achieve zero voltage switching (ZVS) and to prevent shoot-through currents. DM and CM outputs of the NBDD modulation can be expressed after sum the conversion with the following double Fourier series or DFS expressions. As you can see that in my presentation, where the equation 1 that shows that the effective sampling frequency of the DM output signal is doubled without increasing the transition of frequency on the output, and all harmonics around odd multiples of the switching frequency are eliminated. However, the CM output in equation number 2 reveals some drawback, as the frequency spectrum of the NBDD output contains the odd harmonic of the switching frequency and their even intermodulation IM components. The CM output's components are present at full scales, even at a very low level of the modulating signal. And now, SPICE simulations and experimental studies are used to compare the parameters of the proposed Class BD amplifiers with the balanced CM output in the AV prototype. Using the optimal NBDD modulation scheme, all Class BD amplifiers were tested for two different frequencies. F sub C1 is equals to 328 kHz or F sub C2 is equals to 164 kHz. Using it with each switching frequency, two different sets of load resistance as well as the parameter values of the LC output filter. In number 1, R sub L is equals to 4 ohms and L is equals to 15. As you can see in one, since the proposed amplifiers is in figure 4 and 5 are built in complementary MOSFETs and applied supply voltage in VDD and 24 volts exceeded the DVX max voltage in quality number 6. It was necessary to use a voltage level shifting circuits with a Zener diode VZ is equal to 6.2 voltage to lower the control voltage from the gate driver output, with the exception of the MOSFETs whose source are connected with the half voltage VDD divided by 2, i.e. virtual ground 0 volts. So in figure 6, AB shows that the time waveforms of the PWM control signals generated in one selected period, TC, as well as the drain current of the power MOSFETs in figure 4 and 5 respectively. Optimal turn-on delay times of the transistor are adjusted by selecting the resistance of RGN and R sub GP. So here is the number A diagram with Class BD amplifier shown in figure 1 with the conventional NBDD modulator, and in the diagram letter B, Class BD amplifier shown in figure number 2 with extended NBDD PWM modulator, and in C, Class BD amplifier shown the figure number 5 with extended PCM PWM modulator, wherein 1 is equals to RL equals to 8 ohms and the F sub C is equals to 164 kHz. In number 2, RL is equals to 4 ohms, F sub C is equal to 164 kHz, and number 3, RL is equals to 8 ohms, wherein FC is equals to 328 kHz, and RL equals to 4 ohms, FC is equals to 328 kHz. That's all. This is Cheska Loretizo from BS Electronics 3A reporting the module number 3 performance, which titled NBDD waveform diagram. That's all. Thank you.